Thank you, Robin. And thank you. I welcome you here today. I'm going to just start up front and sort of get to what I'm trying to do and tell you that. Okay, we're going to go back to some basics because I believe that the basics haven't changed over time. That the atmosphere does what it does. We're on the receiving end of that, the anticipating end. What has changed, and I think that this is an accomplishment of human beings, is that we, on the science side, have studied, investigated, and basically unlocked the secrets of meteorology and oceanography to a degree. Okay, you may disagree with that, but that's okay. You're on the sea, you're experiencing it. I do know that the quantification that we use in order to look at our forecast skill, to examine, to improve, has never ever been where it is now. That a 6-day forecast is where 6 days in advance, 6 days from now, is the equivalent at the start of my career of a 2-day or a 3-day forecast. So in 25 years, we've stretched out the skill window for forecasts, typically for major weather systems, out almost 4 days. That means that you no longer should be just looking at 12 hours or 24 hours. You should be looking and taking into consideration not just the next front, not just the next weather system that you're facing, but the evolution after that. Because it's conceivable you avoid one thing and you've set yourself up for the next. I enjoy working with this community because you're knowledgeable, you're experienced, you might not like this, you're slow moving, which means, and you're very weather vulnerable. Slow moving means that you have to make decisions in advance, or you're going to be on the receiving end of weather. So the back to basics is to sort of boil back. We also live in a communication era, and communication meaning that you have a plethora of information, if you have the capability on board, to download. You can download and use the same numerical model forecasts. You call them grid files or gridded files. That's just a file format. That would be like saying, PDFs, or PPTs, PowerPoint. It's just a file format. It's just an international standard, gridded binary format. It's the same information that we use to generate forecasts. The difference is, in my organization, and most organizations work this way that have responsibility, is that we use a plethora of information. That we not only use all kinds of satellite information, which I'm going to let you see the world over the Atlantic Ocean through what my office, basically the way that we look at things. I can get a kind of an idea as to the type of information that we have. But we use not just one numerical model or one answer, we use a multitude. So we compare models, we settle on what we think is going to happen based on the behavior of numerical models. We're very familiar with the skill of numerical models. So the forecast that you get is basically a summation of that. One thing too that I will say, that in the marine world, as far as forecasting goes, we sort of have a philosophy. We have failed you if we're not telling you well in advance of something. If we decide to issue a gale warning 12 hours before it happens, we feel like we failed, because we feel that we should be doing that at 24, at 36, at 48 hours as soon as we can. Doesn't mean that we're going to overwarn. We're conscious of that, especially when it comes to the severe events, storm or hurricane force. We really feel like we failed you if we're issuing something because we get an observation confirming our worst fears, okay? We're no different than you at that point if you're the one experiencing that. So just sort of a philosophy, okay? So that's my summary slide. So let's go ahead and start. So I want to take you back to basics. I want to take you back to something beyond just looking at beautiful wind fields from a numerical model, and I want to look at sea level pressure. So we're going to start with that, talk a bit about the basics of fronts, how they relate to sea level pressure. I'll talk a bit about highs and lows. And you'll see this isn't necessarily in a sequence. It's kind of mishmash as it goes along. I do talk briefly about what the weather pattern means, what the guiding currents mean in the atmosphere. The atmosphere is a river. It's actually made of like rivulets. We call them jet streaks. but what the pattern is and why weather systems do what they do. So I'm going to give you a hint of that because I don't really have time to, I can't teach you all about meteorology in an hour and 15 minutes. And I'll have one slide just basically making some recommendations, putting it all together. I want this to be interactive. If you have questions, please ask. If you have comments, please make them, because I'm here for you, okay? It's kind of the same philosophy we have at work. I serve you. You're at sea, I serve you, okay? Same thing, okay? And I will do a shameless ad, but basically, and many weather services obviously have websites. On the lower right there is basically our website, and we have information for the entire North Atlantic and North Pacific on our website. Okay, so many weather services across the globe, we do similar things, and one of the things that we do is a very basic production is we analyze sea level pressure over the global ocean, okay, over the northern, typically over the northern hemisphere. And so not only do we, my office's product for the North Atlantic is there in the upper left-hand side. I will use this in the upper left-hand side. This is our North Atlantic analysis. For the same time, our UK colleagues are producing the same type of graphic, a little bit different, some a little bit of a different philosophy as to how it's done, but representative of the sea level pressure. That's what the contours are, isobars, lines of equal pressure, and fronts. Those are boundaries, temperature boundaries. They also are the focus area for winds, okay? Okay. So our colleagues in Japan at the Japanese Meteorological Agency, same kind of analysis that we produce. In South African Weather Service, SAWS, produces also for their area of responsibility. And this is an example from Brazil. And there are many other nations that do this type of thing. It's a commonality across the globe that these type of things, that this sea level pressure is produced and used. Now, these are analyses. Analyses mean now. Basically means you freeze time and you do an analysis, takes about 2.5 hours on our part, and then that is released. So we've frozen time and give you an indication as to where things are. Forecast is out in time. That's an anticipation, a prediction, okay? We've made sure, as have other services, that our forecasts, graphical, look the same as this. So you can start with this and then go out in time and anticipate the evolution as things proceed. A numerical model does the same thing, where a numerical model takes in a whole bunch of data, most of it from satellite, most of it from polar orbiting satellites, low Earth orbiting satellites, integrate, basically define the initial state of the atmosphere, and then use the equation of motions and physics to go forward in time and predict out 5 days, 10 days, 15 days, 30 days. Okay, so if you can understand how to interpret an analysis, you can then understand how to anticipate how the weather is going to change, because you'll see these features move out in time. I'm going to walk you through a low as we go along. Okay, so we go back 1861. Sir Robert, actually wasn't Sir, I'm sorry, Admiral Robert Fitzroy, who served as basically Darwin's captain on Beagle. He was the captain of Beagle, and he had been the captain of Beagle prior to that as a hydrographic surveyor in one of the most challenging places in the world, Tierra del Fuego. So he got to experience relentless weather for a period of time, and felt that he sort of had his theories about meteorology and how weather systems moved. It's no coincidence that some of the leaders in meteorology early on for development lived in very active places. Norwegians, and I'll talk about them in a little bit, but also the British, who were all over the world. But in particular, Admiral Fitzroy, who was in a miserable place, but learned from that experience. So he came up with a theory, and this kind of proves the theory, and is that he believed that weather systems were actually waves that were in the atmosphere moving, and that you could track and anticipate the weather associated with those waves by using a barometer and looking at the change in barometer, the change in barometric pressure. He noticed, like others had noticed, that the change in barometric pressure actually is related to the wind. Unfortunately, the wind and the barometric pressure, the difference in pressure, so the change in pressure in a pressure trace, it's a one-to-one relationship. This change is actually the force that drives the wind, and I'll go into that. Okay? So the change in pressure is what drives the wind. Okay? That's the force that drives the wind. Okay? So unfortunately, the reason why I say that is because it's a one-to-one relationship. When the pressure starts to change, so does the wind. So if the glass starts to fall, you will see a response in the wind. Okay? If it falls very, very rapidly, the wind is going to go right along with that. And the seas might be a little bit delayed with that, but not by much. And that all depends on the wind strength and the rapid increase in the wind. Basics. Okay? The first warning service was set up by Robert Fitzroy and what became the seedlings for the UK Met office. It was born at the same time that telegraphy, that being able to communicate over distance, occurred. So a warning service that was located in London to issue marine warnings to the coastal sites in northwest UK required communication, barometers that were placed up and down the coast, the information from those barometers sent to London, London watching the barometric traces, and then turning around and issuing warnings based on the change in the pressure, communicating that back. My own organization, the U.S. Weather Service, we started as the Weather Bureau. Our seeds go all the way back to the Army Signal Corps. Why? Because communication and meteorology go hand in hand. It's a two-way street. Not just communicating the message, but also receiving information in a central location, deciphering it, deciding with it, and going back the other way. So the idea of waves, you can see here, this is actually the 1962 storm in the Pacific Northwest. There was a predecessor to that storm. A barograph trace falls to a trough and then rises again. There's a sharp rise, high wind, and then a gradual rise, the wind drops, and then another sharp fall and a very, very sharp, wrong way, very, very sharp rise. Extreme winds in this area here. This was a very, very destructive storm. So this is kind of an extreme case, but it illustrates the point of the rhythm of the weather and weather systems passing. Okay? Okay, so the definition, cold-hearted definition of barometric pressure and what it means. It is the pressure exerted by the atmosphere as a consequence of gravitational attraction, exerted upon the column of air. So in other words, the barometric pressure at the bottom of the atmosphere is a reflection of the weight of the atmosphere or the density, the integrated density aloft above that site. Okay? It doesn't mean that the temperature necessarily is the same, but it means that the makeup of the atmosphere for places that have the same pressure, that the total weight is the same. Okay? So directly above it. So in other words, pressure basically is a reflection of the three-dimensional structure of the atmosphere, all in one value at the surface, the bottom of the atmosphere. Okay? And it reflects all the things that go on the atmosphere, but the biggest contributant is temperature. Okay? Density and temperature are related. Okay? So if you have a cold air mass, it's dense, then you have higher pressure. It weighs more. Okay? If it's a warm air mass, it's the other way around. Okay? Go ahead, Mike.
How about the influence of humidity? How humid the air is? Is that a significant contributor compared to temperature?
Not significant as compared to temperature. Actually, it's kind of a, one thinks that we're adding humidity to the atmosphere, and therefore, because we're adding something that, water vapor, for instance, okay, that by adding it, that it would weigh more. As it turns out, the water vapor is less dense than dry air. So when you add humidity, then you actually are displacing dry air. So humidity, even though it feels miserable to we human beings, it actually is less dense. So humid air, warm humid air, is less dense than warm dry air. It's why baseballs fly out of the Wrigley Field in the summertime. It's not just wind, it's because the air is actually less dense. Yeah, it's why, anyway, so, yeah. Sorry, I couldn't come up with a soccer one for that or a football one, but, So temperature is the main contributor to density, okay? Especially low down in the atmosphere, okay? So temperature down low, near the surface where we live, is what contributes the most to density, okay? So temperature then, related to density, is related to pressure, okay? The difference in pressure is wind, okay? That is the force that drives the wind, okay? So basically, you can skip all the middle and go right to temperature distribution basically is what drives the wind. So changes in temperature indirectly are what drives the wind speed, okay, and the direction, okay. So basics. So what I have up here is, this is a sea level pressure analysis, similar to what I showed you earlier. It's not the same one. This is actually of a time when Gonzalo was just passing over the Hibernia oil field, which is right here, right underneath the storm, and was off to its east to come and visit Northern Europe and transition. The yellow lines are the isobars, okay? And I should mention, and I should have mentioned earlier that I had up there, average sea level pressure across the globe is 1,013 millibars. That's probably something you want to remember. The reason being is that gives you sort of an anchor point. So a reference point is when you see that a high pressure system is 1030 millibars or hectopascals, that gives you an idea that that's well, significantly higher than 1013. If you see that a high pressure system is 1050 millibars, that's greatly higher than 1013. It gives you an idea that that's a stronger high pressure system. It also means that it's more dense. It also means that it probably has colder air. Okay? A low, on the other side, can be, if you have a 1,000 millibar low, that's somewhat lower than if it's summertime, that may be a little bit more to be cautious about. In the wintertime, that's really a relatively weak low. But if you have a low pressure system, say, in this case, 967 millibars from Gonzalo, that's significantly different than the 1013, the average. So that means that there's a very strong pressure gradient or difference in pressure with that storm system. And you can see that reflected in the isobars that are spaced at 4 millibars. That's what we do, and it's typically the standard that people do. If you display grid files of this, you can display it any way you want. You can go down to 1 millibar if you want. You can see this gradient right here of pressure associated with Gonzalo as it's moving off to the northeast. And that 967 basically equates to very, very strong winds associated with this storm system, okay, as it's migrating along. A tropical cyclone, basically, it has a purpose. Everything sort of has a purpose, and the purpose is to transport heat and moisture from the tropics and bring it north into the extratropics to sort of, to basically maybe get rid of an instability or minimize an instability by taking an overage of heat and moisture in the tropics and bring it northward. It would be nice if it happened a little bit less violently, but it's just a sign of sort of the instability that builds up and then it has to be released. Anyway, so I'll stop there with that. So there's another thing that I want to show you here is, and I purposely have done this because I wanted to show you basically how our forecasters look at things. We use integrated workstations where we look at everything as overlays. And we do that on purpose because there's a lot of strength in that. If you have multiple screens, and I'm sure that some of you do this, you know, when you have electronic charting devices and all, that you're looking at multiple screens with information, that it does make it a little bit more difficult to go from one to another, especially if you have, you know, a bunch of tabs and you're flipping from tabs and all. So we do it in an integrated fashion. And so the satellite imagery that is underneath this, clouds basically, kind of reveals some things. Okay, for instance, and we'll go through another example like this. This is a large area of high pressure. You see a difference between the high here, a 1029 high, and the 967 low. There's a pretty good pressure gradient across there. These clouds here that you see in this area, those are cumulus clouds, or stratocumulus, meaning they're low clouds. They don't have a lot of vertical extent. They're probably not raining, or if they are, they may just be virga, especially over the ocean. that basically it's a large area of fair weather. In this area, it's clear. Basically, what's happening here over this high, air is subsiding, it's sinking, okay? It's not coming down quickly, it's just gradually coming down to the surface, okay? As it's sinking, it's drying. It's drying, it's not gaining moisture at all. It's not condensing, it's not cooling, it's warming, and it's drying. Okay, so that's why there's a large area of sinking. The character of the high is different than a low. A low tends to be sort of efficient, consolidated. I mean, even though they can be very, very large, the difference is that a low basically is processing air the other way. Air is going up. Right? Let me just finish one, and so air is going up by vertical up means that it's cooling. By cooling, it means that the humidity, relative humidity rises and condensation occurs. So there's no coincidence that you see clouds associated with a low pressure system and you see minimal clouds or very low clouds in this case and no clouds here in a high pressure system. Subsiding air, drying, warming. The other way, rising, cooling, condensation. Not cumulus nimbus, cumulus. Any puffy cloud, even if it has limited vertical extent, if it's puffy, then it basically is a cumulus cloud. If it's precipitating, it's a cumulus nimbus. Now, there's a whole range of that, everything from severe thunderstorms and all. Not in this case. These are relatively low clouds. They're pretty in the imagery, and it's kind of hard to tell the vertical extent. We have other instruments that we can look at in order to do that. We can look at the temperature of clouds and see whether or not, and what you would see is that these are very close to the temperature of the ocean underneath it, okay, indicating that they're very low clouds. Okay. I would say stratocumulus over the ocean are connected to high pressure. That, I mean, when you say, there are a variety of different, I'm talking specifically about stratocumulus clouds, okay? Sort of small, puffy clouds that are very shallow in extent, okay? Okay, thanks. Okay, if we weren't on an Earth that was rotating on this wonderful globe sphere that we're on, the blue marble, what would happen is if we had a difference in pressure, that a high and a low, this is a different low, Gonzalo has gone off, actually is up here somewhere on its way to Europe. If we weren't on a rotating planet, then what would happen is highs would fill lows. The instabilities would basically be filled, and that would be done with it. I don't know how you'd get to that point, in the beginning where you get the difference, but anyway, that because we're on a rotating Earth, there's a deflection, basically, of the wind. The force that drives the wind is the pressure gradient, the difference in pressure. So in this case, there's a 1026 high here, there's a 973 low, just coming off the Labrador coast. So high to low, the pressure gradient force is perpendicular to the isobars, so is in that direction. If we weren't rotating, then the wind would blow in, fill the low, and be done with it, okay? Nature isn't like that because we're on a rotating planet. There's a deflection of the wind from the pressure gradient, and that's caused by us being on a rotating planet that's a sphere, or thereabouts a sphere. Okay. So instead, the winds blow inward towards lows and outward from highs. Remember, lows, condensation, upward motion, precipitation. Okay? So air is coming in some fashion, rising, cooling. The moisture content stays the same. The relative humidity increases. The amount of moisture stays the same. The temperature drops till eventually the temperature of the parcel that's rising and the humidity temperature, the dew point temperature, when they're equal. If you keep cooling that, something has to happen because the temperature will not drop. So it condensates, basically creates cloud, and then cloud creates precipitation. The processes sort of take over. So in this infrared image, where you can see cloud top temperatures, basically, the white is cold, So this gives you an idea as to up in here where there is sort of an organized area of, this would be stratus cloud, very high cloud, and precipitation. So that is forced in an organized way by air flowing into this low center. It doesn't flow in, like in a tropical cyclone in a donut. It actually follows the fronts along, the temperature boundaries along. Okay? And it's actually quite structured and repetitive, which is nice. The high on the other side of it, subsiding air flows outward. And the winds tend to blow from, if this is the pressure gradient here, the winds tend to blow across the isobars. So not like this. Whoops, I apologize. There. Not like this into the low, but they flow about 15 to 20 degrees across the isobars, from higher pressure to lower pressure. So from, this would be a 1024 isobar right here, 1020. So the lower pressure is in that direction, so the winds tend to blow across about 15 to 20 degrees across the isobars. Okay? So if you have a map of isobars alone, you actually have an indication of what the wind field is. The tighter the isobars, the higher the pressure gradient. The higher the pressure gradient, the higher the wind speed. So now you have both wind direction and an indication in a relative sense of the wind speed. The tighter the isobars, the higher the wind. The weaker the greater the distance between the isobars, the weaker the wind. Okay, back to basics. Okay. Okay, so let's take a little bit of a diversion. I only have 2 slides that have words on them. I have one right at the end, but I want to show you, to try to take a little bit of a step backwards. I've kind of gone to basics for a reason. There are things that you need to do that I think that you need to do aboard ship, and you probably do these. One of them is that routine observation of weather, both internally, for your own logbook's sake, for education purposes, for accountability, but also if you have the opportunity to share your observations through the the International Volunteer Observing System program, then that is a real plus, because that means the information you have doesn't just sit with you. It actually gets to me, my office, my colleagues in the Met Office, my colleagues in the Bureau of Meteorology in Australia. It's shared globally, okay? If you transmit that information, we know what you're experiencing, okay? And sometimes what you're experiencing, what we think you should be experiencing, aren't quite the same thing, okay? So you're sharing that information. That's a key, okay? Aboard your own vessel, weather is part of everything. If you're going to make decisions, weather is just something you have to factor in. You know, are we going to do a boat drill at this time? Okay, well, what are the conditions going to be like? You know, in your planning process, in your day-to-day, in your normal watch routine, weather is something that has to be factored in. It has to be discussed. How did conditions, when you're doing watch change, how did conditions change during the previous watch? Are they changing as anticipated? How are they expected to change in the oncoming watch so that they have an idea as to what to expect? And are they happening as anticipated? Sometimes things happen. We never seem to remember when things happen more slowly. We certainly remember when things happen more fast, more quickly, and that we've had to react to something. Anticipation, if you're able to do that, especially with the vessels that you have, that's a really good thing. Okay. Use a barometer. Use a microbarograph. Watch the trace. Relate that to the wind as an educational, but then also as just a practice. Relate that. Get familiar as to how the pressure changes with fronts passing and all. Pressure fall, pressure rise. The character changes because it depends on what the front is like, what the structure of the front is. Okay? Teach your students to read the water. It's just inherent part of being a sailor. Is read, basically, make sure they know how to read the wind, an idea of the Beaufort scale, who, by the way, Sir Francis Beaufort is the one that asked Fitzroy to do the voyage. The voyage, by the way, wasn't centered around Darwin. It was an opportunity to sort of bring the flag around the world, and Darwin was a passenger, basically, as a scientist. So he wasn't commanding the ship as, well, we needed to do this. He took advantage of an opportunity. Beaufort actually set up that opportunity for Darwin with Fitzroy and had that in mind as basically contributing to science. But he came up with the scale. There's some claim that perhaps he adapted a scale from predecessors, which is fine. He got the credit for it. Doesn't matter. It works. I'm a sailor. I use the Beaufort scale all the time. and it works. Visualization as to how the ocean is changing, that reflects back into what the wind is doing, because there is a one-to-one relationship there. Okay. Relate the local conditions to the bigger picture. One of the things that you should be doing, if you have, you can do it electronically, or you can do it, if you print it out. Take the surface analysis or the surface forecast, mark your position or where you're going to be. Okay? Have an idea what to expect in the future, but have an idea also what's going on now. How close is that front to you? Have you measured the distance? How fast is the front moving? Is the front even going to come through us? That type of thing. Be hands-on at doing things. Don't just look at a screen, with values on it or wind barbs and just assume that that's what's going to happen. Okay? Because you might not have that screen. If your communications go down, you might not have that information. Okay, just as a prep. So place your position on the analyses. Do it routinely as an educational tool, but then actually as a practice for yourself as you're going along. And one thing that I have here is share the information with your crew. Okay, that maybe not sit so well with some people. That's fine, but it's an education process. I flew in the cockpit of a plane one time as a passenger in an airliner, and the captain turned around to me and says, "You have a set of eyes just like I do. You're up here. You're part of the crew. You contribute." I think that was a lesson to me. It scared the hell out of me because, closure speed is pretty amazing. But basically, sing out if you see something because you have a set of eyes. Sometimes you see things one way, they may see something different, and they may ask the question, 10 times it might be annoying, but that 11th time, it might actually be, why is this happening? I didn't notice that was happening. You might not tell them that, but anyway, that's just, respect that. Okay, so wind is the force, okay? Pressure gradient drives the wind, and wind is the force. Wind is the destructive force. It's why we call storms storms. It's why hurricanes are so damaging, because of the force of the wind, okay? It is the power. It is what builds seas, okay? Wind waves, swell. Swell is wind wave that has migrated away from its generation area. In the west coast of the United States, west coast of North America, even in Alaska, in the summertime, when conditions are relatively calm locally, when we don't have a lot of wind, we have swell. That swell is generated south of New Zealand, or actually south of Australia in New Zealand, and migrates all the way northward. Africa receives swell from the North Atlantic, and actually some of that swell can actually make it south of the Cape of Good Hope into the Indian Ocean. North Atlantic's winter swell can be felt on the southwest coast of Australia. The ocean truly is global. That energy, that pulse of energy that's generated from a storm in the North Atlantic or in the North Pacific can affect areas far, far, far away. We had a swell event years ago on the south coast of Long Island and on the New Jersey coast in the Atlantic Bight. That swell was generated on the west coast of Africa, the west coast of South Africa. And it's easterly flow, and then that energy came and basically caused riptides and rescues. So it is a global ocean and related. So swell is just wind wave that has moved away from its source and continues to propagate and lengthen in the period, the distance between. You've been at sea, you know that at times you can have multiple swell patterns. It's complex. It's something we're going to get better at. We're actually pretty good at it in the basics, but we're going to get better at it over time because we realize how significant it is. Also, wind drives storm surge, whether it be in the North Sea, whether it be in the Atlantic Bight, the New York Bight with Sandy that we had, whether it be with a tropical cyclone making landfall. The wind is the main contributor to storm surge. It's the focus of pushing the water. Okay, so it has a lot of different negatives. It's also your power in order to move. Okay, so let's quickly just go through a couple of different places here. This is the same analysis that I started with. So what I have here, let me start with this one here because we're going to talk about this in the next slide. Okay, so the purple arrow here, if this is the point of interest that we're looking at, so 1,016, 1,020 millibars, so basically 1,008 because 18 because it's right in between. Okay, so this is the point. this is the wind direction along that point. So the pressure gradient, which is the red arrow, is perpendicular to the isobars. So the pressure gradient is that way. The wind, or the parcels, are deflected by the fact that we're on this rotating planet. And this is the Coriolis force that deflects the wind from this direction into this direction. There's another force that acts on it, and the ocean, even though you might not think it, there's actually friction from the ocean. There's more friction over land because winds tend to be lower over land because there's more friction. Over the ocean, there still is friction, especially when you have high seas. And it's something we found out on the science side, that friction is a significant factor that needs to be accounted for in tropical storms and tropical cyclones. The reason being is it actually restricts the strength. If we don't account for that friction, they call it wave drag, if you don't account for that, then your model basically overdevelops the storm. You need to throttle it back. It's almost like the wave drag is a governor, basically, on the tropical cyclone. It slows the wind speed down just a bit so that the strength of the storm is not as, it doesn't increase as, there actually is a limitation as to how much it can increase. Okay, so again, pressure gradient, friction, Coriolis force, and that's the main point here, the relationship between the isobars, pressure gradient in that direction, and this is the wind vector, basically. So the direction that it is flowing, and the speed is determined by the distance between the isobars. So let's look at an example. So same location is right here. This circle is, and you should know how to read these, that there are 1, 2.5 feathers on, you could think of this as an arrow shaft. The location of the vessel is right here at 1,018 millibars. This is the product. If you come across the Atlantic in 2017, this is a product that you'll be able to download and use as you're coming across. This is issued by my office. The Met Office does something similar without the observations, but we all kind of contribute to the same kind of thing. So again, 1,018, so 1, 2.5. A full feather here, or line, is 10 knots. So this one has 10 plus another 10, so 20.5. That's 5. So that's 25 knots from the south. We describe wind as the direction it comes from. If you're an oceanographer, a current is the direction in which it is taking you. The conventions are opposite. It's always fun to sit down with oceanographers because they hate this convention. And I throw sailors under the bus. I do say I'm a sailor, but I say it's because it makes total sense. A northeast wind, it's blowing from the northeast. Okay? That's important to a sailor. Sailors, I believe, are attributed to figuring out how to define wind, okay, the direction. So I throw you under the bus every once in a while. But I'm a sailor too, so it's okay. It's fun to aggravate oceanographers. So 25 knots. Here's another one over here, and I had this one. This is 20 knots, 1, 2, 1,022 millibars. And in this case, the wind is almost in the opposite direction, is a north-northeasterly flow. And you can see how that relates to the isobars that are here, 1024, 1020, 1018, or 1016 rather. It's 4 millibar spacing. So again, relating the wind to the pressure, basics. Okay. So pressure gradient is the source. So with that being said, on this satellite image with the isobars, if you look at the isobars, tell me where you think the winds, where the strong winds are. You don't have to be shy. 2 o'clock? Okay, so that would be in that area? Yeah, actually, excellent, good. Anywhere else?
To the north of the low.
To the north of the low, right in here. Okay, let's take a look. Okay, we live in a pretty neat age. The satellite information gives us a lot of variety of different things, okay? This is data from 2 polar orbiting satellites called METOP, the European satellites operated by EUMETSAT in Darmstadt, Germany. And the METOP series of satellites have a variety of different instruments on them. One of them is something called a scatterometer. It's a space-based radar that looks at both sides of the satellite. So in essence, the satellite, in this case, is flying in this direction right here, right in this area. right smack in there, right in there. And it's two satellites, so it's a little bit, it's not as clear as it could be because they're overlapping. But, so as it is flying, there are two instruments, radars, that are looking out at angles to either side of the satellite, okay? What it is measuring is the roughness of the ocean surface, okay? The roughness, you're a sailor, the roughness that your eye sees. The rougher, the dark shading of the water, those are gusts that are coming at you, right? Well, this basically measures over a larger footprint the roughness of the ocean surface. If you can do that, then you can also, if you do multiple looks from different angles, forward and aft, then you can, at the same point, you can not only see or determine the wind speed, you can actually determine the wind direction, make an estimate as to what the wind direction is. Okay, if you look in a radar, you have your sea clutter knob. Okay, when you try to take out the sea clutter and remove that, okay, upwind and downwind are quite different because the wave shape is different. There's a harder face on the front of the waves, the smaller waves, okay? There's a sharper face than on the back. When you look downwind, you don't see as much clutter. When you look upwind, you see clutter. That's the premise of this data. So in other words, this is wind, basically. So these are actually arrows of wind. You can kind of get a hint of them, but they're very dense. They're at 12.5 kilometer resolution. So let me just quickly, 20 knots is the dark blue, 25 is the light green. The dark green is 30 knots. And there actually are some yellows in here. The scale is up here. That's 35 knots. So there's some gales in here along the Maine coast, up farther to the northeast, and then south of New England. So there's a large area of 30 knots of wind. And we saw the gradient is tight right in here. That's where we see some of the strong winds, and also here in the northwesterly flow. Okay. Similarly, we talked about up here at 2 o'clock with higher winds with a strong pressure gradient. There's 35 knots winds in here, a large area of 30 knots, and an even larger area of 25 knots. This instrument measures wind up to about 80 or 85 knots, but it has to be on a scale that the instrument measures. So if you have 85 knots at a point, and the instrument measures like this, that's not what it's going to see. But if you have 85 knots over a large area, then about 12.5 kilometer wide, then the instrument actually does a pretty good job at that.
If it only measures the wave pattern, it should be different depending on the temperature of the water, the density, the currents, eddies, stuff like that.
Yes. Yes, okay. First of all, what it measures is it's the capillary waves. So it's the same thing that you kind of look at for looking at the small scale features in the wind, okay? So that's a really good thing. So it's not confused by swell and that sort of thing. That's not impacted because the wavelength that this measures is much smaller. Okay, so it measures that. So that's a really good thing. Is there an effect due to current? Yes, it's relatively minor, but there is an effect due to current. There's more of an effect due to the temperature difference between the ocean and the atmosphere. Okay, if the ocean is warmer than the atmosphere, then the ocean is heating the atmosphere, the lowest layer of the atmosphere where we all live and work. And there's an overturning, basically, there's an instability. So that's gustiness, basically, is if you're basically mixing the lower part of the atmosphere. Okay. On the other side of it, if you have warm air over a cold ocean, then you actually, what happens is the surface layer that we all live and work basically starts to decouple. It's not longer attached to the lower part of the atmosphere. So the effect of this is that you will actually see, in a southerly flow off the east coast of the United States, you will see the north wall of the Gulf Stream. You'll see it because it is a sharp wind difference. And the wind difference is that there's strong wind over the Gulf Stream. This is in southerly flow, okay, warm air moving northward. And as soon as you go across, there's a stability that builds up low in the atmosphere, and the wind speed just drops. Okay. Now, it doesn't mean you have tall ships, literally with tall masts. You may actually be sailing off of whatever is up high. Sorry, I don't know exactly the language as to what it would be, but top gallant or whatever it is, that you may actually have 25 knots of wind up there. and it may be glass on the surface, okay? That's pretty cool. That's another reason why I like interacting with you guys, because you get to experience this stuff. And then we confirm it 30 years later by a satellite. Okay. But I wanted to show you this because it's a way that we look at storms. This isn't constant. Basically, this is a satellite that's rotating around the Earth. It's actually flying pole to pole, and the Earth is turning underneath it. So twice a day, we get a look like this across the global ocean. So, and the satellite, it's kind of agnostic. This is an Atlantic view. If you're sailing in the Southern Ocean, if you're along the Antarctic coast, the Antarctic Peninsula, same thing. As you get coverage, and especially it increases, you can see that the gap between the satellites actually closes the farther north and south that you get. It's the same thing as farther south. So we actually get a lot of information in places that we used to get nothing. I'm fascinated by this area up in here, Cape Farewell, because the wind screams. It is the windiest place over the global ocean in the wintertime. It's not in the Southern Ocean because it's persistent there at that location. Another place that's neat is actually right off of here, where you can see northeasterly flow that there's can be gale force, persistent for days upon days upon days. We have a similar situation in the west coast of the United States, Cape Mendocino area, Cape Blanco up off of Northern California. Okay, so I talked early on about, about grid files, and this is actually the way that our forecast is. This is wind speed, the same coloration that I had on this slide for the same system at the same time. So you are going to go back and forth, and I just want you to sort of get a feel and compare back and forth where you see the scatterometer winds and where you see these winds, and get sort of in your comfort zone to see what the differences are. And so let's go ahead and go back and forth. So that's the scatterometer, or scatterometers. And the idea is just to color match. And you might see some subtle differences. For instance, this is a little bit stronger wind out in here and here in the scatterometer, but not much. Even what looks like the patchiness of the wind in the grid file is basically reflected in the scatterometer data. It kind of gives you an idea as to where we've come. It gives you confidence that the numerical model actually, it's not tuned to the scatterometer, but they both kind of, one uses the other and effectively. So kind of gives you an idea that we actually know a little bit more than certainly we used to. When I started, we just had isobars, and we used to hand plot and measure things, and it's quite a bit different. Okay, so I'm going to talk about fronts, and then I think I'm going to just jump to sort of the end, and maybe we can discuss things. And I do want to say that it's these smaller waves that the scatterometer is measuring, not the larger waves. It's the smaller noise. It's on the 5 centimeter scale, so anything about this size is what it's measuring. So it really is measuring the impact of the wind. If you had a bigger wavelength that you were measuring with the radar, then you get caught up in basically measuring waves, and that's a whole different ballgame, because then you get a reflection of the swell. Okay, so fronts are boundaries. Why do you care? Because wind shifts, temperature difference, weather, rain, thunderstorms, fog associated with fronts. The thing that I want to drive to you is that it's a temperature difference. If you think back earlier on, temperature and wind go hand in hand. Temperature difference, pressure difference, density difference are basically what drive wind, okay? Fronts are boundaries of temperature difference. And typically, the way they're described is, and we'll use this cold front as an example right in here, is the way that a front is described is it is on the warm side of the temperature difference. So for a cold front, that means this is the cold front, then the cooler air, the transition zone, is on that side of the cold front, okay? The pips, in this case the triangles, they point in the direction of motion. This is an occluded front, which is kind of more like a warm front, or in this case is kind of a little bit more like a cold front. It kind of depends on the character. So the temperature difference would be back here, and this is the leading edge of the cold air, or the trailing edge of the warm air in here, okay? And you can see that associated with this density difference, this temperature difference, is a pressure trough. A front lies in a pressure trough. The trough exists because there's a density difference. There's also, in here, you have very strong southeasterly winds, And then there's a very weak pressure gradient behind that front, back in here. So you'd have strong winds southeasterly going around to probably southwesterly. Maybe you have 30 knots out of the southeast and going around to maybe 15 knots out of the southwest. Okay, a transition zone. Okay. So I mentioned Norway earlier on. Well, the sign of the times back, we use the frontal terminology because basically meteorology and the times back in 1914, 15, 16, basically was a war footing in Europe. So a zone of clash or a zone of transition basically was considered to be a front. So meteorology basically took on the language of the war that was ongoing, the horrible war of the First World War, with trench warfare and clear lines between the two sides and a transition zone in between. So they took that language. So our our Norwegian colleagues back in 100 years ago examined storms that came through Norway and basically came up with a theory as to the evolution of a storm system. And they came up with what they call the Norwegian cyclone model, which is still used today. They were phenomenal meteorologists, actually were oceanographers that had transitioned to meteorologists. So, in quick, they described a low, and this is from Bjerknes and Solberg's paper in 1922, that they described this as a warm front with a warm sector. So cold air here, and on the trailing edge of the cold air is the warm front. Cold front here. The circulation is indicated by the arrows, and the low pressure system is right in here. So you could think of in this case, they sort of had the isobars and the streamlines that are portrayed here were quite similar. They showed what a cross-section through a front looked like, and a warm front slopes forward. So you could think of it as sloping this way. I apologize for that. It's sloping this way. And the classic idea of high clouds, cirrus clouds, sort of clear air, then cirrus clouds, and then the cloud bases reduce. Eventually, close to the front, you have an area of precipitation right in here. The warm sector is typically cloudless, or thought to be cloudless. And then here's a cold front that has a completely different shape to it. It's more like a wedge, more like this, as opposed to a sloping, sort of gradual sloping warm front. So a sharper front, and if you've been through cold fronts, which I'm sure you have, that they can be incredibly sharp and incredibly very rapid transition with some significant weather associated with them. Some are a little bit softer than that, certainly, that most of them are softer than that. But so that thought really hasn't changed. I mean, the frontal theory still exists for reasons, because it actually was a really good theory in the beginning. The important thing about a front is that it separates air masses of different temperature, but it also has other characteristics associated with it. It has a pressure trough because it's a density difference, because it's a temperature difference. It has a change in wind direction, it has a change in wind speed. A moisture discontinuity, cool, dry air replacing warm, moist air, or vice versa. And it has a characteristic cloud and precipitation form, sort of gradual descending cloud precipitation, and then a sharp, or with a cold front, you can have a very sharp line of thunderstorms that are coming along with it. This is a very clean example. This is actually, this line right in here, this is temperature difference is what you're looking at in color, okay? This is a model representation at very high resolution of what a front looks like. It's a mess. This is the front right here. There actually is a predecessor to that in the numerical models. It turns out, you look at the satellite imagery, you can see these things. This is a 3-kilometer model that we run in the US. Other nations do similar things or even at higher resolution. But that zone right in there with a very, very sharp temperature gradient, that's the front. Okay, the leading edge of that is front. That's where the wind shift occurs. But you can see the characteristic is quite different, both along the front, the sharpness of the gradient, where it may not be, the colors, the more colors, the sharper, okay? And also the depth of the zone of transition into the cooler air, that it actually has pulses that are in behind it. These are more the things that you experience, and it's very, very difficult for us to, we're still stuck a little bit in the old days. This is hard for us to describe to you, because we're still trying to understand it. But we do see this. We see this in the pressure trace and all. Okay. Classic, on the surface analysis, the classic symbols that we use for highs and lows. A trough is a density, an area of density difference, but not strong enough to be considered a front. But it can have weather with it. It can have showers. These pulses that we've been having here, that with the rain that come through, those are troughs. Okay? They're embedded in the cold air. The cold front came through a couple days ago, but these are basically enhanced areas of temperature difference that sort of get born over the ocean and then come ashore. That's kind of what we're experiencing here. We call post-frontal conditions or post-cold frontal. So a warm front, red, with pips that are curved or half circles. Cold front, and the motion is in the direction that the pips face. A cold front rather, with triangles, typically because cold blue is sort of synonymous with that. A stationary front is a stalled boundary, a temperature boundary that actually is stalled and not moving. It can be strong. Just because it's not moving doesn't mean that it's not a strong boundary. It can have strong wind and weather associated with it. Typically more of the warm frontal type weather with fog and cloud. And an occluded front can be sort of a mix of either the characteristics of a cold front or a warm front. Occluded was originally thought that it was basically the cold front overrunning the warm front and that cold air basically moving aloft. It doesn't quite work that way. It actually is an extension of the warm front and then encircles the low. So let's talk a little bit about storms, and I think I'm going to probably I'm a little bit slower than I was yesterday, which is fine. So I'm going to stop at a certain point and jump to the last slide. And I'm not going to get, unfortunately, to the weather pattern. But let me go ahead and I'm going to walk you through a storm in about 5 minutes and kind of give you an idea as to how it evolves. So these are in 12-hour segments. We're going to focus on this 1016 low right here off of the mid-Atlantic coast. And we're going to follow this along as it moves out into the North Atlantic, out into this area. Okay? Stationary boundary. A little high that's going out in front of it. There's a stronger high, a larger high that's building in behind it. And let's follow this along in 12-hour segments. Okay, so here it is at this time, 1013, 12 hours later. We can still see the high out to the west. You can sort of see that the stationary front is extended farther out to the east. Again, a temperature boundary that's pushed out. 1013, we use a tracking mechanism. So this is expected to be 24 hours from now. This is the position that this low is expected to be at 1,004 millibars. So intensification, 1,013 to 1,004. And if it's intensifying or the pressure is dropping, assume that the pressure gradient around that low is going to increase. And what does that mean? The wind's going to increase. Okay? Okay. So the low moves off, and now is 1,009, 12 hours later. So it's dropped from 13 to 9, 4 millibars. Is expected to be here in 24 hours after this time, and 988 millibars. That's a big fall from 1,009. This low is about to go through rapid intensification. In fact, it will go through what we call explosive development, where it doesn't fool around. It does its thing. It really intensifies. Okay, starts out as about 30 knots. Eventually, this storm's going to end up as hurricane force.
Is there anything that can be seen in this display that foreshadows that intensification?
Well, aside from the track and the fact, because this is an analysis, what you would couple this with is a series of forecast charts. 1 day, 2 day, 3 day, 4 day, out in time for you to anticipate. This is when you mark down where you're going to be. If even this low is here, traveling in this direction, where you don't want to be, even at this time, it's slow motion, is up in here. So anticipation, that means have an idea what to expect, not just from now, but in the future, even several days in the future. Okay? That would be the indication, basically. From this, there are indications that we have. It would be too late, basically, for you, with the speed that you travel, in order, if you were out in this area, to really do anything. Okay? So pre-planning, this is October, North Atlantic. That tells you something so there's a whole lot that has to go in ahead of time in order for avoidance. But there is an indication, basically, in the cloud structure that shows you that this is going to rapidly intensify. Okay, so 12 hours after that, we've 24 hours expected, it's developing hurricane force. No longer, it's just jumped from gale to hurricane force, meaning that that's going to reach that, anticipating in 24 hours with 964 millibars. It's 1,002 now, so it's dropped 7. You can see that the structure of things has changed, that the storm system, the orientation from being linear now is amplified, is more upright, north-south. And that's because basically a low is a temperature wave. It's a wave of temperature boundaries that then encircle. So in essence, it's a temperature eddy that evolves over time. It starts with an area of basically opposing wind and then wraps up in time and encircles itself. It's a vortex. Okay, 12 hours after that, developing hurricane force, 987 millibars. This is the Hibernia oil field here, which has very high elevation anemometers on their rigs, but there's 55 knots right there. The flag indicates 50, and there's 5 after that, and anticipated to slow in the next 24 hours down to 952 millibars. Keeps going. This, again, is the point where you don't want to be, is in here. The occluded front wraps around the low, and the gradient is extreme right in here. That's where the strongest gradient is, and that's where the winds are the strongest. And still, as it turns out, in between this time, you'll see, is 948 millibars, hurricane force. Again, this area in here, you can see how the structure of the fronts are, where there's a change in the wind direction because there's a trough. There's a change in the isobars direction, but also there's a strong trough because there's a temperature difference with the fronts, and there's wind shifts with the fronts. Here you would have southwesterly going to northwesterly or westerly, eventually going to northwesterly. Up in here you'll have easterly, southeasterly, going around to southerly, and then rapidly going around to westerly to northwesterly if this low were to transit over you. So the idea of using surface analyses, back to basics, to supplement other information that you have, if you're using grid files, which I actually encourage, but to balance it with sort of the old basics. There are reasons why things happen, and to stay in touch with the way things evolve. Let me end with this. I know it's just an hour at this point. So the Norwegians came up with a wonderful cyclone model that exists and still exists. Over the oceans, there were experiments done off the east coast of the United States with our European colleagues, actually the global community, worked to try and understand these explosive deepening cyclones, okay, one that I just showed you. And they came up with a version of the Norwegian model. A gentleman by the name of Mel Shapiro and his colleague Dan Kaiser adapted the Norwegian cyclone model and came up with this diagram to show some of the differences, but also it's in my mind, this is the validity of typically what happens over the ocean. So 4 different steps of the evolution is a frontal wave. Remember, it's sort of horizontal where there's a boundary. The cold air is here, the warm air is here, and that wave amplifies. The temperature wave amplifies, and that's what these lines are here. These are lines of temperature. So here's sort of a little bit of a wave in here, and then it amplifies. It starts to wrap up and break, and then encircle around. That's this phase here, and then eventually it actually curls, okay, in on itself with warm air pooling in the center. So what these structures, lines, the fronts basically, the reason why I show this because it really shows you where the wind is, okay? So up in here to the north is where you'll have wind, that's the stronger gradient. Same thing here, and then with the fronts, okay, back behind the front, but especially up in the northeasterly flow. Many cyclones don't go through the full evolution, but they get to this point. And in the northerly flow, this is where if you were transiting, your pressure would be rising very rapidly, and so would the wind. That you would go through a sharp transition of relatively weak, say, southwesterly winds to strong northerly. Skies would clear rapidly as you transition this zone, and it would scream out of the north. And the full-blown cyclone, it's this area right in here where the strongest gradient is, where the strongest pressure difference is, where the strongest winds are. And this is typically where we see the strong storm to hurricane force winds. So let me go ahead and bring it to you. Let me go to my last slide. I'm sorry for this, but this is fairly, you just don't know what's going to happen. Okay, 1, 2, 3. And these, you'll have these available so you can walk through them. So use all the available sources that you have available. Don't just rely on one source, even though we're in an age where the forecast skill has never really been better. I mean, we anticipate weather systems now a week in advance. You should too. Use the information that's available in order to, if you're in planning mode or whatever, you should, whatever you do, don't start looking at the weather when you're heading down the channel. Okay, that's a mistake in this day and age, especially when you're working in the fringe seasons, but meaning fall and spring, but even in the summertime. Okay, you need to factor it into your decisions sort of continuously. Use a variety of different things, the grid files, certainly, but don't rely just on that. The basics still work, and in fact, they're better than they've ever been. Don't be afraid to use the basics. Plot your position, get in touch with that. Get in the rhythm of how things are evolving. Don't wait until things start to go sour to then kind of get deep into the weather. Just make it part of your routine. Okay. Aboard, weather impacts everything that you do. Okay. Could be something as simple as what you're going to have, what the cook is going to have for dinner, just because if you're going to be bouncing. Okay. I went to catch a bowl of soup one time that was climbing out of the pot when I was driving tugs. I did catch the soup. I didn't catch anything else in the galley. Everything else was in a pile down below. The cook went back to go shut his porthole. He came back and really thanked me for, I saved the soup, the tomato soup, you know, the $1.99 can of soup. But I didn't get burned either, so that was a good thing. Use weather as a teaching opportunity, not just for your mates and crew, but then also for your students. But engage your mates and crew in, not necessarily the decision process, but the information process. Couple things is, one thing, if you're hurt, if you're a master and you're hurt, it may be a little bit difficult for you to do things. Also, it opens up because they may have something to contribute. Doesn't mean that it's, you know, that you say, well, let's vote. No, I'm not suggesting that at all. But information exchange. I mean, in the old days, weather information was kept like this. You know, I work with captains that way. Don't look at that. You know, don't. That's not your job. Okay, well, if you're responsible in the wheelhouse, guess what? It is. It is your job. Okay. Use a visible display of weather information. It may be that you post things if you have the room for it. I know that if you're a smaller vessel, that may be difficult. You can do it electronically. But make it so that you have a reference quickly to look at. I mean, it's sort of the world we're in. I mean, we do this with our cars now with GPS. That, you know, I don't feel lost without a GPS, but I actually like having that sort of extended view. Even though if I know where I'm going, because it gives me an idea. Or if it has traffic on it, then I can tell where I don't want to go. Take weather observations, but locally, for your log, but also do it to contribute, okay? Because we use that information all the time. It's still important, and it will be for a long time, because you're there, okay? Know your vessel tolerances, procedures. Know what to expect and when to change things, okay? Bad weather, factor in fatigue, seasickness, okay? If you're sailing with a limited crew and now you see numbers dropping, your options are getting narrower and narrower and narrower. It's a factor that you have to consider, especially if you're preparing for an event, a storm, and then you have to go through the event. You may be exhausted in the preparation process, in the anticipation process, okay? Get everything ready. Now you've got to go deal with the storm, okay? And people are already dragging. You have to factor that into decisions. Okay. Again, I'll state what the science is, that we really have, you're at a golden age, I would think, of weather prediction. Okay. I was at a conference in Montreal, and there was a discussion about maturing of weather prediction, that we're seeing the horizon of the, not the end, but we're seeing the horizon of the big challenges are basically being achieved as far as weather prediction goes. Climate is a different story. That's a completely different story. What the challenges are now is conveying to you and us learning what is the impact of weather, how do you make decisions with the information we provide you. is the information that we provide you, aside from just isobars, is it what you need in order to make decisions? Okay? What language do we use to give you a heads up? I was on a conference call during Sandy where one of my colleagues basically asked the department, actually the deputy mayor of New York, he asked him, we have laid out to you what we consider to be catastrophic. What are your actions now? And he apologized before saying that because we were out of our comfort zone. And the mayor basically said, thank you very much, this call is over. And that was that. 10 minutes later, the mayor of New York was on TV and they were evacuating Zone A. That to me, when I talk with him, I mean, that's the epitome of a career. He couldn't contribute much more than that, my colleague, basically, but he stepped out of his box because the language we were using, you know what, it wasn't good enough. Basically, we didn't couch it that way. Well, the numbers are going to be this, da-da-da-da. That's not what you wanted to hear. They wanted to hear, this is the worst thing that we've ever seen. This is beyond our wildest dreams as far as being horrific. What are you going to do about it? We need to learn how to do that a little bit more. Not to beat the drum in a bad way, but basically to convey information that's useful for you. So that's where the challenges are going to lie in the future. So let me finish there. I really appreciate your time.